I can push record. Okay. Thank you. Okay. Good morning, everyone, and thank you for your attendance despite being in midsummer period. Today we have Alex Cloninger as our presenter. Alex is an associate professor of mathematics at UC San Diego. He received his PhD in applied mathematics from the University of Maryland in 2014, and subsequently he was an NSF postdoc in Gibbs assistant professor at Yale until 2017 when he joined UC San Diego. His research area is geometric data analysis and applied harmonic analysis, with focus on modeling data using locally lower dimensional manifolds. With that being said, I'll leave the stage for Alex.
Awesome. All right. Thank you for the invite. Hold on. Okay, cool.
Excuse me, Alex, sorry for interrupting you. So if you had any questions, please use the chat box and I'll ask your questions while Alex is giving us.
Yeah, feel free. I'll try to look at the chat as well and we'll just go from there. Okay, so like Mohammed said, thank you for having me. Like Mohammed said, I'm at UCSD in math and also in the Halıcıoğlu Data Science Institute. I always like to give a little plug for it. Pretty fun data science institute, very multidisciplinary, a lot of cool research coming out of there. Yeah, so anyways, what I'm going to be talking about today is a collection of works around a theme, which is building data representation, in particular, nonlinear data representation, from a single pass of the data. So I'm just going to briefly show a slide of collaborators, thanks to NSF and Intel and stuff like this for funding. In particular, I'm going to talk about work that Caroline has driven, Varun has driven, and Andreas has driven. Varun and Andreas are two students of mine, and Caroline is and work that Jinji has done, who's another student of mine. And then Caroline's a postdoc who's going to be starting at UNC in the fall. Okay, so what am I saying when I'm thinking about data in a single pass? All right, so normally when people want to think about nonlinear methods, you usually would think about things like kernel methods or building lifting to a high dimensional space. But there are a lot of problems that one would have if you want to apply these in a setting where data is, say, distributed or where data is streaming, right? Namely, storing, loading data points can actually be a quite memory intensive thing, right? So maybe you need a high throughput of the data. Maybe your data is distributed across computers and there's not a high bandwidth for communication between the computers, even if to just a central source. So the problem in this setting is that most nonlinear methods that one would want to use are actually quite difficult. For nonlinear classification or function regression, you have to build some huge kernel matrix. That's going to be expensive, doesn't work in a streaming fashion. If you want to build statistical distances, that means you have to load bunches of data points onto a central server. So this is sort of a regime where I'm kind of interested in trying to build up some interesting algorithms. So domains of application that I'm trying to think about are, like I said, most kernel distance methods require loading pairs of points. We're going to say, all right, can't do that here. Many random feature space models to get around this require floating point storage. Maybe that type of storage isn't conducive in a memory limited environment. And so what I want to think about is basically how to get around a lot of these problems in various disciplines, let's say. So the theme of the talk is basically how do we develop nonlinear methods that can be computed by just taking a single pass across my data. So what I mean by that is like a mini batch, right? Load in a little bit of data, do something, throw it away. Load in a little bit of data, do something, throw it away. Or compute something on each individual computer and then just send that aggregate statistics so that you can then, work with that. Okay. And in all of this, I'm going to be talking about how to keep things efficient in terms of computation, in terms of storage, you know, but also still trying to understand rigorously what we're doing and sort of what is the, you know, mathematically, what are we really accomplishing? Okay, so this breaks up into 3 topics, and hopefully I'll be able to get to all 3. If not, I might wind up having to skip the last one. But basically, what I'm going to look at is features for approximating Wasserstein distance in a single pass of our data, the optimal transport or movers distance. This is distances between distributions. Binarized reproducing kernel Hilbert spaces and ways to do nonlinear kernel methods in, you know, 1-bit storage. And if we have time, I'm going to talk about doing kernel regression in a streaming setting where your data is coming in one at a time, and we can have some streaming model that, you know, doesn't require computation that scales with the number of points. So that's where we're at. All right. So the first topic I'm going to talk about is some work I've been doing the last couple of years on optimal transport, and specifically what's called linearized optimal transport. So what's the question that we're trying to address here? So most people, when they think about a classifier, think about a problem where they have a point that's in a vector space and a label. Okay. I want to think about a different problem. I want to think about a problem where a point is not just a point in a vector space, but it's actually a distribution. Okay, maybe a distribution supported on RD, or equivalently a point cloud. Okay, so the problems we're going to think about here are that you have a point cloud and a label for that point cloud. An example of this could be like shape matching. You know, a shape is a point cloud and that has a label. Right? So this is actually really important in a large number of applications, and I think it's kind of an understudied problem, to be perfectly honest. So, you know, this is the general setting. If I want to, I want to talk about how to build a classifier on a distribution. It's not even really clear what that means, right? Yeah, so what we're going to look at is how to create embeddings of point clouds where we can build classifiers, but where we still maintain some really good understanding of what this embedding is actually doing. Okay, so examples that I'll talk about moving forward. One example is this type of problem shows up all the time in medicine, for example. Flow cytometry is one example. You draw somebody's blood and you treat it with some chemicals, drop it one cell at a time. Each cell gets some 7-dimensional representation. So because of that, a person is now a 50,000 point cloud in 7 dimensions. And that point cloud tells you whether or not you have leukemia. Okay. So that, and whether you have leukemia is the label. So that's kind of a setting that we're thinking about here. Another setting you can think about is actually image processing. You can think of images as being, well, the way most people in deep learning think about it is that it's, a point in 784 dimensions. But another way to think about it is that an image is just a density on the unit square. So if we think about it from that perspective, maybe we can do something that's a little bit more geometric. Okay. So this is a setting. So we're going to talk about we're going to talk about distributions and distances between distributions. So for me, there's a natural way to think about this. What is the natural way to define distances between distributions? It's optimal transport. So if you're familiar with optimal transport, the next couple of slides is probably going to be pretty boring. If you're unfamiliar with optimal transport, I'll just give you like a high-level overview. Optimal transport is basically the following question. Say I have a distribution, I can think of that as just a pile of sand. And I have another distribution, I can think of that as like another pile of sand. Okay? And I want to think about the optimal way to move each piece of sand from one cloud to the other. Okay? And when I say optimal, what I mean is I want to find the way to do that, to transport one cloud into the other. I want to find a way to do that that requires the minimum amount of work. And by work, I mean like the physics definition of work, distance times time, or force times distance. So optimal transport is a very natural distance between distributions. And I'm in particular going to focus on one, which is called Wasserstein 2. So Wasserstein 2 distance is the following. It says of all the ways that we could move some distribution mu to some distribution nu, right? These T's are what I'm going to call transport maps. I take each piece of sand and I look at how it gets transformed into the other distribution. I look at how far I had to move that piece of sand, and I integrate across all my pieces of sand. Okay, and that is the Wasserstein distance, distance squared. Okay. So this is the idea, and you know, what we're actually going to be interested in is actually going to be the argument of this. What is the transport map itself? How do I optimally transform one point cloud into another? Okay, and that's going to be denoted T mu nu. Now, if you are familiar with optimal transport, you might be stopping me and saying, well, wait, how do you know this is going to be a function? This could be a coupling, all this. I'm going to make the assumption that the source distribution is absolutely continuous and satisfies some nice properties. I'll get to why that's not a problem in a minute. But because of that, I can always assume that this is going to be some function. Okay. So this is called the Monge problem. There's a Cantor-Borge problem we're not going to get into now. But broadly speaking, this is the distance we're going to think about between distributions. Okay. So the beauty of optimal transport is that it scales sort of correctly with the geometry of the space. If you shift your distribution a little bit, the distance grows as the size of the shift. If you rescale your distribution, the distance grows according to how much you rescale the distribution. Con is that this is incredibly slow to compute. Okay, you have to solve a linear program every time you're going to try to compute an optimal transport between two distributions. So let's think back to that problem I was just saying, which is that I have like a bunch of distributions distributed. Well, if I wanted to compute all pairwise distances, that would require me to do n choose 2 optimal transport computations. That is completely intractable. Okay. And beyond that, I said that we were going to talk about learning, like supervised learning. Wasserstein 2 gives you a distance. It's not clear how you can turn that distance into something that you can build a classifier on. Okay, especially in a way that would be efficient. So this is roughly the problem that we're interested in. And what I'm going to do is give you kind of the solution, and then we'll talk about what the solution actually can do. Okay. So the solution is instead to think about what's called linearized optimal transport. And the way that this works is actually pretty clever. And by the way, I should say, it's clever. I was not the original person to propose this. Someone, Gustavo Rode originally came up with this proposal. He developed a couple of algorithms. What we've done is extended the algorithms as well as built a lot of theory about what this is actually doing. Okay, but here's the idea. Okay, I have all these distributions floating around in space. What I'm going to do is I'm going to create a fixed distribution sigma. Okay, it can be anything. Think of it as just being like a Gaussian. Okay. And now what I'm going to do is I'm going to find the optimal transport, not between mu I and mu j, but from sigma to mu I, and then from sigma to mu j, and then from sigma to mu k. So it's like spokes on a wheel. I'm finding the optimal transport between each sigma and each distribution. Okay. And what I'm going to store from that is not the distance, but the map. How did I transform sigma into mu1? How did I transform sigma into mu2? Okay, so mu is now being mapped to the transport map. So this is linearized optimal transport. Okay, and the idea, the way I like to think about it is that mu I and mu j, these two distributions, there was no registration between them. I didn't know if they shared any points in common. I didn't have like anchor points or anything. What I'm doing is artificially creating anchor points. I'm saying, all right, I have a map from sigma to mu1, I have a map from sigma to mu2, sigma to mu3. For each point in sigma, it goes to some corresponding point in mu1 when I do this in an optimal way. And it goes from sigma to mu2 in some optimal way. It goes from sigma to mu3 in some optimal way. Well, now I have a registration. Because now the star went here, the star went here, the star went here. I'm going to think of those three little regions as sort of being aligned. Okay. And now we can start talking about what we can do with these features. Okay, so this is kind of how I think about the problem. But it leads to some questions that I think are quite critical. So the first question is, how do I build All right, well, actually, first off, I should say, now that I've mapped mu to a function, it's a function in a Hilbert space. Theoretically, I can build a classifier on that. I can build some off-the-shelf classifier. Okay. And also, I can define distances, right? Now that I have this transport map from UI, I have this transport map from UJ, I can just take the difference between them, Euclidean distance, just integrate across sigma. In this image, it's basically how much did the star move? What's the distance between the stars? What's the distance between the triangles? What's the distance between the hearts? So that really no optimization. So this classifier theoretically could be built, and this distance theoretically could be done and would be fairly cheap to do, way cheaper than computing an optimal transport between the UI and the. But there's a bunch of questions. What can I build for a classifier? How can I transform mu and still have the classifier be kind of robust to that transformation? And what does this distance even mean? How is it related to the optimal transport distance? Okay, these are the types of questions that I'm interested in. So with that, let's talk about it. Let's talk about what we can do, okay? So I need one piece of formality before we can get into the results. That piece of formality is what I'm going to call a compatible transformation. Okay. So what I'm going to look for are sort of a bunch of group actions I can do to distributions that will interact nicely with optimal transport. So roughly the way to view it is this sort of diagram, commutivity type diagram I have here. I could map sigma to mu using optimal transport. That's the optimal transport map. And then I could push mu to S push mu. Think of S as being like a shift, right? So then I move mu over to the side. That's one way I could go from sigma to S push mu. Another way I could go from sigma to S push mu would just be to do the optimal transport between sigma and S push mu directly. Okay. What I'm interested in is, all right, this was the optimal way to get there. This was a roundabout way to get there. When is the roundabout way about the same as the optimal way? That's the central question. When it is the optimal, when the roundabout way is the optimal way, that is a very, very nice S. It's very easy to work with. Okay. So we call that a compatible transformation. Mathematically, what it means is if you transform mu with some function h, it's the same, and then take the LOT embedding. It's the same as taking the LOT embedding of mu and then transforming that function with another function, composing them. Sorry, that should be a composition, not a star. So, okay. So examples of this are shifts, scalings, and some combination of shifts and scalings. So these are what I call compatible transformations. And compatible transformations satisfy this really nice property. Namely, if I have a convex set of compatible transformations, a convex set of shifts, a convex set of scalings, they're compatible with LOT. Because of that, if I did the LOT embedding of each one of those resulting distributions, mu shifted again, mu scaled again. If I do the embedding of all of those distributions, that set is going to be convex. Convex in push forwards goes to convex in LOT space. Okay, that's critical. Also, we could have this idea of what I'm going to call almost compatible, which is that, okay, it's not the optimal way, like doing an optimal transport and then applying a function is not the optimal way to do it, but it's not too far off. Okay, that's what we're going to call almost compatible. Examples of this would be perturbations, right? You have a mu and you have some perturbed version of mu. The action that gave you that perturbation is almost compatible. Okay. And this satisfies another simple statement, which is basically that if you have something that was convex, delta compatible, then the resulting embedding is going to be almost convex. Okay. So these are sort of nice preliminary results about compatible transformations, but I want to talk about how to use them. Okay. So this is going to be kind of the family of things we can do to a distribution. We can shift it, we can scale it, we can do some combination of shifts and scalings, we can perturb a distribution. Okay. And what does that give us? What it gives us is the following here. Let's say that my reference measure was absolutely continuous, caption, whatever. And I have some family of actions I'm going to do to some distribution mu. And then I have some family of actions I'm going to do to my distribution nu. Okay. So now I've got a bunch of data points, a bunch of point clouds. I have mu, I have shifted mu, I have rescaled mu, I have perturbed mu. Those are all labeled ones. And then I have nu, and I have shifted nu, and scaled nu, and perturbed nu. Those are all labeled minus ones. Can I build a classifier? So here's what we can say. I have all these data point clouds that were like mu, all these data point clouds that were like nu. If there was a minimal separation between all of those point clouds in Wasserstein distance, then when I do LOT embeddings, those two sets are going to be linearly separable. Okay, linearly separable. I don't need to build a complicated classifier. I need to build a hyperplane. That's it. That's kind of surprising, right? Honestly, this surprised me. that you don't have to build a complicated classifier. Very, very, very simple classifiers will be able to tell the difference between all of these different mu's and all of these different mu's. And we can be hyper precise about this. Under certain assumptions on mu and nu and shifts and scalings and perturbations, we can write down the exact constants we need for how much minimal separation there had to be in terms of, pretty simple optimal transport type constants. Okay, I won't go into the details of that. Let's just say it can be made precise. So that's a pretty cool result. And there's another result that we can say as well. Let's say, again, that sigma is absolutely continuous. And let's assume that the mu, I call it tau here, I probably should call it mu. The mu that we're going to be moving around is also absolutely continuous. Nice, smooth, convex support distribution. Very nice distribution. Well, then it winds up, if I did this LOT distance, which remember, that's just distance between one transport, distance between the features, Euclidean distance between the features, of a shifted version, a scaled version, a perturbed version of the distribution, and some other shifted, scaled, perturbed version of the distribution. That distance is Halder 1/2 continuous with respect to the original Wasserstein distance. So that means that if I do my LOT embedding and then just compute Euclidean distances, those distances are going to be almost correct. They're going to be almost the same as if I had done n choose 2 Wasserstein distances. If I'm only considering shifts and scalings, forget about perturbations, it's an isometry. They're identical. So if you have a problem where you have point clouds shifted and scaled, you can do an LOT embedding, and you will have an isometric embedding of the Wasserstein distances. Okay. Which is really nice from a computational perspective, because now, rather than having to pull each distribution off of some computer and compute an optimal transport between all n choose 2, I just need to solve n problems, one on each computer, send the features that I've created, and now I can just compute easy Euclidean distance. Okay. And I should note that if we remove a lot of the assumptions on the distribution, we can still prove that this is still pretty stable with respect to perturbations. Okay. So that's a family of results that we had between Caroline and I on this idea of an LOT embedding. We extended this actually to say, you know what, there's actually a lot more you can do. So my student Varun and Harish, they wound up proving that there's a much larger set of compatible transformations, even more things we can do to mu that will wind up falling into this whole theory. of allowing us to say that we can approximate the distances, that we can build linear classifiers. So the technical assumption here, I have a picture in a second that'll give it a lot more clearly. The technical assumption is that the optimal transport from sigma to mu, you look at the eigen decomposition of the Jacobian, and you're allowed to scale along the principal directions, pretty much arbitrarily. What does this say in practice? What this says in practice is, if I tailor my reference distribution, right? Before I was just saying sigma could be anything. If I pick my reference distribution to be an example of mu, then it broadly opens up the amount of compatible transformations I can do. It'll allow me to scale and stretch and shrink mu in a bunch of different ways, and that's still compatible. And because we're going to think about, having sigma be an example of the mu, it motivates the idea of having multiple references. Okay, so this is the example that I find to be a lot more intuitive. If I pick my sigma to look like my mu1, then I'm actually allowed to shear in principal directions. So all of a sudden, transformations between mu1 and mu2 here would be considered compatible. That's not a shift, that's not a scale, it's a shearing in different directions, but it would still be a compatible transformation. And then the multiple references, that's basically the idea that I find the optimal transport map from sigma 1 to mu and from sigma to mu 2 to mu, and I concatenate them. And that's my LOT event. And everything I have said about linear separability, about computing distances, also applies in these settings. Okay. So that's kind of the rundown of all of the theory. I want to step back for a second and think about what this means in terms of the original question, which was, how does this help us for distributed computation? Well, now I have a classification model, which says that if I applied a bunch of different push forwards to mu, I'm going to classify them the same way as mu. Oh, sorry, I saw that there's, I'm going to classify them the same way as mu. So if I had an example of a perturbed mu, a shifted mu, a scaled mu, a sheared mu, all of those things, they'll be classified the same way as mu. So what this means, again, is that I can build a hyperplane that will classify correctly. Now in practice, this is still a function, right? So that's still kind of an infinite dimensional object, but it's a very, very, very simple smooth function, which means we can sample sigma to discretize this to some finite dimension. And then, because we're only trying to preserve pairwise distances, we can do some kind of Johnson-Lindenstrauss embedding that says that we can reduce the dimension to log n dimensions. So if I have n distributions on n computers, I can do a LOT embedding, sample the LOT embedding, Johnson-Lindenstrauss to reduce, and all I need to send is log n pieces of information, log n bits, basically, well, log n floats for my centralized computer. And all of a sudden, I can build a classifier, I can build distances, everything I want. That works in a low communication bottleneck environment. Okay. So that's the idea. So let's talk about how this actually would work in practice. So I want to give an example. All right, I'm going to make a little harder problem than, I'm a mathematician at the end of the day, so I'm going to show an example from this. But we're going to make this a little harder. Okay, so rather than just having ones and twos that we're trying to classify, I'm going to involve shifted versions of ones and scaled versions of ones. So my data is actually a 1 up in the corner, a huge 1 over here, a tiny 1 down here, a huge 2 here, a small 2 here. Okay. And now what I'm going to do is an LOT embedding of each one of these, right? Because like I said, an image can be thought of as just density on the unit square. So I'm going to do an LOT embedding of all of these. And because I need to build a linear classifier, it's not hard, which means I don't need a lot of training data. Okay, so here's what we get. This is the number of examples of training data. that I get from my 1s and 2s. 60 examples, not too many. These are randomly chosen examples. With only that small amount of points, my classification error has reduced to, 3%. Okay. So this is better than if I had done PCA as a dimension reduction. This is better than if I had built a convolutional neural network. Okay, everyone likes to say convolutional neural networks are translation invariant. They're not. This proves they're not. What we have is actually translation invariant. Okay, and scale invariant, and perturbation invariant. And on top of that, these things are linearly separable. This is a two-dimensional reduction. Yeah.
So when you, for the translating the MNIST images, how have you translated? Because it is very focused on one digit.
I drew random examples from MNIST. And then along with that random example, I applied a scaling and a shifting that was randomly drawn.
Yeah, but so does it mean that part of the digit is going to lie outside the boundary? Because
good question. No. We define the scaling first, bounds on the scaling, so it stays inside the image. Once we've decided the scaling, we then define the shift so that it remains inside the image.
I see. Okay.
Yeah.
So you apply scaling all the time.
Yeah.
To make sure. Okay.
Yeah. So we're not destroying the image. I'll show another example in a minute of this. But yeah, so what I wanted to say was that this is dimension reduction, linear dimension reduction to 2 dimensions. You see that there's a linear classifier. It really is a linear classifier. That's all that's needed. So I also said that we could have shearings. So now I can shift an image, I can scale an image, I can shear an image. So this is examples of, 7s and 9s. And this is examples of extreme shearing between 7s and 9s. Okay. And what we get is, so this is again, the number of training images that we use in the classification error. We wind up being able to greatly reduce the classification error very, very, very quickly as a function of the number of points we sample. Because again, it's a linear classifier. Okay. So this is, this is pretty nice. This is saying that, and by the way, I should say there's a lot of work that we're doing extending this. Because we're building a linear classifier, we're currently building an active learning framework. I don't have a slide on this here, but basically we can show that if you're clever in which points you ask for the labels for, you can build a near perfect classifier with like 10 labeled examples. Okay. And you can do active learning. You can do everything you want from a linear model. Because that's all we need is a linear classifier. Okay. I just wanted to give one more example related to flow cytometry. This is early work, but I wanted to show it. So again, there was this example. If you have a point cloud for a person, it's in 9 dimensions. I think it's 7 before. And this is an example of a person that's healthy, and this is an example of a person that's sick. These are 3 of the 9 dimensions. You see that it's pretty hard to tell, right? There's weird features going on here. But what we can do is just build an LOT embedding. So how would you transform the uniform distribution into this point cloud? How would you transform the uniform distribution into this point cloud? We get these transport maps. We do a PCA reduction to 25 dimensions. So now each person is just a vector in 25 dimensions. And I build a linear classifier. And in the linear classifier, with 15 examples of healthy people and 50 examples of sick people, we can get a test accuracy that's in the 90th percentile in terms of both precision and recall. Now I'll be honest, AML is neat. This is an example of detecting AML, which is easy as far as flow cytometry is concerned. But still, the fact that we can build this 25-dimensional vector of a complicated distribution and build a linear classifier that has a 95% accuracy, near 95% accuracy, that's pretty good. Okay. So this is ongoing work, but I'm saying this to say that there's a lot of cool examples that we can there are a lot of interesting directions that I'm wanting to move with this. This is sort of just the beginning of this LOT work. Yeah, so this is one sort of direction of research that I've been taking recently. So we have these nice pros about how distances reflect optimal transport. You don't have to do and choose two distances. We understand the distances in the embedding space. You know, learning classifiers is easy. So now we're working on active learning of these classifiers. Obviously, a con is that LOT is still expensive to compute for each distribution because it's a linear program each time. So we're working on incorporating what's called entropic regularization or sinkhorn distances. That is actually a really fast algorithm. And we're about to put up a paper that proves that everything that I've just said also applies to sinkhorn. Okay. So this is sort of a line of research, right? That again is motivated by this idea that I don't want to compute all pairwise distances. Okay. All right. So now I'm going to go into another line of research that we're starting to consider. So changing up the question a little bit. All right. We're back into the easy setting, which is that we want to build a classifier where you have a point in a vector space and a label. Okay. Now, normally the way that you would do that is you would build a kernel. If you want to build a nonlinear regression, kernel ridge regression or something, you build a kernel between all n points. That's an n by n matrix of all pairwise similarities. Okay, this k, x, y. And then you do some sort of inversion of that matrix. You can use it to solve for a regression, nonlinear regression. So here's my question. I want to build features of my data point such that when I just take inner products of one data point and the other, I get this kernel. Okay, or approximate. So I want to understand this nonlinear relationship between points, but I want to do it where I don't have to do all pairwise distances. And more importantly, I actually want to think about it where I actually have a quantized feature space. In other words, I don't just want this to be any vector. I want it to be a binarized vector. So I'm trying to figure out a one-bit representation of a vector of bits or tertiary, right? 1, 0, -1. That when I just take the inner product of that vector with another vector, I approximate some nonlinear relationship between points. Okay. And this is going to be really critical for a number of applications. I was describing ridge regression, but this would also be for building a kernel SVM. This would also be useful for building kernel maximum mean discrepancy. That's a kernel measure of a two-sample test between how close these distributions are to one another. So this is kind of the setting. Can we do this? And can we do this in a way that allows us to just pass through our data once? Stream our data in, get a binarized vector, throw it out. Okay. All right. So there's several ingredients to this. I'm just going to give you a rundown of the ingredients. If you're familiar with several, if you're familiar with the ingredients, then I, apologize if this is a little redundant. But first ingredient is what's called random Fourier features. So Rahimi and Recht, about 15 years ago, figured out an initial approach to this problem of not wanting to look at pairs of points. They observed that if you want to approximate a translation invariant kernel, say a Gaussian kernel, you could rewrite that as random Fourier moments of your data and random Fourier moments of your other data point inner product. By random Fourier, I mean you sample random weights from a Gaussian, and you take e to the IWX. And then that gives you a huge vector. For each W, it's in dimension. And they take the input. Okay. And so then you can get a finite embedding. You can turn it, you can turn it into a real thing. It doesn't have to be complex using cosines. So this would be some vector z, where you do z of x, you do z of y. If you took their inner product, you get something that kind of looks like a Gaussian. But I want to go a step further. I want to have this be quantized. This is a float, and it's highly sensitive to being a float. Okay. So I want to think about how to turn this vector into something that's actually just a binary vector, because then I can efficiently store it. So the next ingredient that we're going to bring in is what's called noise shaping quantizer. So this is very electrical engineering focused, right? It was originally designed for sort of something you would implement on a chip to do quantization of streaming data. So what's the idea? Given some alphabet, +1, -1, I'm going to define a stable noise shaping quantizer if I can quantize my stream of numbers coming in. And there's a way to rewrite it, a way to recover the original numbers as like that quantization can be written as the original numbers plus some lower triangular matrix. Basically, it only depended on the previous data. Okay, this has to be a causal filter, basically. It's stable if the size of U is bounded. If the size, or sorry, if the size of the L infinity norm of the bit stream or the stream points being bounded implies that this U is also bounded. That means it's stable. Okay. And I'm going to talk about a particular version of this called a sigma delta quantizer. So when you think of binarizing vectors, probably the first thing you think of is just rounding. If the number's positive, I assign it a 1. If it's negative, I assign it a -1. Scalar quantizers are brutal. They are not stable quantizers. Okay. But we can still define it, right? You just round to the nearest bit. But now what we're going to introduce is what's called a first order sigma delta scheme. So what that says is I'm going to round to the nearest bit, but I'm not going to actually round the thing I got in. I'm going to round the thing I got in plus a running tally of how much error I've already agglomerated. So if I'm getting in a bunch of numbers where, yeah, I can round them to 1, but each time I'm building up error, then at some point, even though I probably should have rounded to 1, I'm instead going to round to -1 to make sure that I keep that error bound. Okay, that's what's called a sigma delta quantizer. First order just means I pay attention to the error from the previous point. Rth order means I pay attention to the running tally of the last R points I've had come in. And this is stable. Okay. So with that, we get to one more thing, which is how do we actually construct an inner product on these bits? So the way we're going to do that is actually by introducing this one matrix called a condensation matrix. I won't go into the particulars of it just for the sake of time. But basically, it is a simple matrix where when I want to take inner products, I just take this weighted inner product between this string of bits and this string of bits. Okay. So that's the idea. It's constructible, it's cheap, it's sparse, you know, everything that we want. But what does it give us? So it gives us the following. Let's say I had a set of points from RD, and I have a normalized shift invariant kernel that I want to, you know, approximate. Then it winds up, I can build a string of bits that encodes X and a string of bits that encodes Y, such that when I take the inner product between those bits, bit streams, the inner product minus the true value I'm trying to approximate is bounded by the size of the bit stream. Okay. So what this is saying is, and plus some other terms that can be controlled according to the size of the alphabet, this parameter that I'm not going to get into. So what this is saying is, we can now take our data, hit it with random Fourier moments, quantize those random Fourier moments. Okay, point comes in, random Fourier, quantize, it is now a binary vector. I just keep all my binary vectors, and if I ever want to compare them, this is the error between that comparison and the ideal comparison we want. Okay, and this is results with Jinji Zhang, who drove a lot of this work, as well as Harish Kannan, myself, and Rayan Saab, who's also here at UCSD. And by the way, also, that's a point-wise bound. We can also do this spectrally. If I have an n by n matrix where I have my true kernel matrix, K, and I have my quantized kernel matrix, and I was wanting to do, say, regularized ridge regression or kernel ridge regression, what we can say is actually that spectrally, this matrix is upper and lower bounded by some constants times the original matrix, which means that I have not changed any of the eigenvalues or eigenvectors too much. Okay, so it's not just a pointwise bound, it's an entire spectral bound. We can be very precise in terms of what these bounds are. So now we have this really nice, oh, sorry, and I should have said, this is with high probability. We're bounding the probability that this is nice by something that goes to 1. Okay, small chance we mess up, not that big a chance. This is saying that now we can work entirely in the feature space. We can work entirely in the binarized space of my data. And the amount of memory that I need, if I did random Fourier features, would be 32 times the number of random Fourier features I took. Because it's, single digit precision, maybe double float would be 64 times m. We can get it down to, if I wanted m features, I have m times b, where b is the size of my alphabet. So if we're doing 1 bit, that's just a 1. We reduce the amount of memory by a factor of 32. Okay. And with that, we can actually show that this works. So let's pick examples. Let's think about doing kernel ridge regression. You have points sampled from the uniform distribution. You have a function, a complicated nonlinear function on that point, on those points. We embed the points, we quantize the points, and then we do linear regression in the feature space. Because linear regression in the feature space of the kernel is equivalent to doing a nonlinear kernel regression. So again, we're doing linear regression to learn this complicated function. And this is how the test mean square error scales as a function of the number of features that we create. And what we have here, this is for binarized embeddings. So I have, 2 to the 10 dimensions, but it's bits, 2 to the 10 bits. Okay. And look at the error, right? R1, R2, and beta are our methods. First order, second order, and then beta I didn't get into. It's called distributed noise shaping. But you see that we get this fantastic mean square error that's beating any other version of binarized embeddings, and that's asymptotically reaching the random Fourier features themselves, the unbinarized versions. We can do this for kernel SVM. Pick some digits, build a 1v1 SVM classifier, look at the test accuracy. Once again, our test accuracy asymptotically goes to the best that it could have been, and it keeps the number of bits small. Again, these are binary vectors that we're building a linear SVM on, because linear SVM in the feature space of the kernel is the same as doing kernel SVM. Kernel maximum mean discrepancy. That says I have 2 point clouds, the red point cloud and the blue or the green point cloud, and I want to test whether or not they're the same point cloud or different point clouds. So this is a statistics test, a 2-sample test. You can get a score called kernel maximum mean discrepancy. It won't go into the details at the moment, but then you can test it with what's called a permutation test to get its power. And what we get is that asymptotically, the power of being able to detect the differences between these 2 data sets goes to 1. We do better than any other method. We asymptotically reach what you would have done if you did the random Fourier features. And again, we're able to stay entirely in the feature space. Kernel SVM, this whole complicated business that I'm not going to get into at the moment of how it works, is actually just doing a means test in this feature space. I have a bunch of binary vectors from one data set, I average them, a bunch of binary vectors from the other data set, average them. How far apart are those two vectors? That's it. Simple linear results. Okay. So this is another direction of research that we've been interested in. We're building on this right now. We're developing better methods to reduce this dependence on M, the number of random Fourier features. We think we have a way to actually significantly reduce the amount of memory needed. Involves some tensor, analysis. But yeah, I mean, it's a pretty fun method. For the sake of time, I'm just going to make a quick comment about this. If you are interested, I'll show you a citation at the end. The last thing that we worked on was streaming kernel regression. If you're interested in kernel regression, you want to think about how that would work for streaming data, we have that, and we have a method of doing this such that it is universal learner, which means you can learn any function on the training data. Okay. So what I want to just kind of emphasize here is that it's really important to think about mathematically rigorous nonlinear algorithms and efficient storage and computation. And at the intersection of those two is a very, very, very rich area of research, in my opinion, that is still developing and has a wide range of applications. So we've got a bunch of ongoing directions that we're interested in. If you want to see what some of these papers are, we've got our LOT paper. This is about to be published in Information and Inference. This one, this for the binarized RKHS. If you're interested in streaming methods, I recommend this paper here on streaming kernel, and we've got code available if you're interested. So yeah, that's about it.
Thank you.
Thanks.
So does anyone have any questions? Yeah, I guess compared to most of the presentations, this was mathematically heavy and a little.
That's going to happen with me.
Yeah, for someone who does not have like clear background. So I have just a quick question regarding the Wasserstein estimation.
Yeah.
In my work, I've used another distance called the sliced Wasserstein distance.
Yes.
Yeah, which tries to approximate, or I don't know if you can call it approximate. I think it is not approximation, but it is a way just to come up with something similar to Wasserstein, but at the same time, you do not need to solve the linear programming.
That's right. That's right. Because on each one-dimensional slice, optimal transport in one dimension is cheap.
Yeah, it has closed form solution.
So so let me just say this. So I mentioned this guy Gustavo Rode, who has developed a lot of the algorithms that initially started LOT. He has what's called radon CDT. So radon is the same as the sliced. CDT is cumulative distribution transform. It's the 1D version of everything I've just described. So there is a method for doing an LOT embedding of sliced Wasserstein distance. Okay, it's called, like I said, radon CDT. The problem is I can't prove anything about it. So, and neither can Gustavo. We've been talking about it. This is actually an ongoing area of research, is how to show similar results that we have for sliced Wasserstein. But algorithmically, what I'm describing does work.
Okay, so in terms of empirical results, can you do something more than SWD, or more or less you can use SWD?
Well, so again, what it's doing now is it's saying that when you take the sliced Wasserstein, normally if you think of sliced Wasserstein distance, it's for computing distances between objects. What we're saying is fix a central object and do slice of Wasserstein between the central object and each example you have.
Mhm.
And that gives you features that are going to be really nice for building classifiers. I can't say that it's going to be able to build a linear classifier. That's the main thing I'm trying to prove it.
Mhm.
But it does work similarly. So basically it says all of these Wasserstein methods you know for building distances, there's also a way to extract features that you can build classifiers from.
Okay.
Yeah.
Okay. Thank you.
Cool.
So, I guess we are almost out of time.
All right.
If there is no question, I guess we can end this session.
Okay.
Thank you so much.
Yeah, thanks.
Meet you soon. Bye.
Yeah.